Thanks for tuning in. I'll be discussing temperature-dependent interactions between parasites and gut bacterial symbionts of bumblebees. My basic question in this project was how temperature influences infection by modulating interactions between parasites, hosts, and the core gut microbiota. Temperature and symbiotic microbiota are two factors that can affect host resistance to infection. A common response of humans to infection is fever and elevation of body temperature. Other animals also use behavioral or metabolic methods to elevate their body temperatures when infected. These high temperatures can directly inhibit parasite growth or potentiate host immunity, and can reduce infection in mammals, reptiles, and insects. Symbiotic gut microbiota can also improve resistance to infection by acting as physical and chemical barriers to parasite establishment. If temperature and microbiota can each affect infection on their own, how does temperature affect the balance between symbiotic and parasitic microbiota? I broke this problem into three main questions. How do parasites and symbionts differ in thermotolerance? What are the effects of temperature on parasite-symbiont interactions? And how does temperature affect infection and gut microbiota in live hosts? I first used cell cultures to characterize the temperature dependence of parasite and symbiont growth rates and antagonistic interactions. I then tested the hypotheses generated by cell culture experiments by measuring the temperature dependence of infection in hosts. I'll be focusing on interactions between parasites and symbionts of bumblebees, which are important pollinators of crops and wildflowers, especially under colder conditions in which smaller bees are unable to fly. However, some species of bumblebees are threatened or in decline in the Americas, Europe, and Asia. Infectious diseases may be contributing to these declines. Two factors that could support resistance of bees to infection are their thermoregulatory abilities and core gut microbiota. Bumblebees have remarkable thermoregulatory abilities for insects of their size. They are facultatively endothermic during flight and incubation, able to maintain body temperatures more than 30 degrees above ambient. This enables them to fly even at temperatures near freezing. Both bumble and honeybees harbor a core gut microbiota that is consistently dominated by bacteria from just 4 genera. These bacteria are acquired via social interactions in the colony and can enhance resistance to gut infection. I focused on the parasite Crithidia bombi, a trypanosomatid that infects the hindgut of bumblebees. This parasite is both prevalent and widespread in multiple bumblebee species on at least 3 continents, and has deleterious effects on queens that attempt to found new colonies in spring. However, the bumblebee gut microbiota have been shown to increase resistance to infection. Crithidia bombi and other trypanosomatid parasites of bees have recommended culturing temperatures of 25 to 27 degrees. Recommended culturing temperatures for all 4 genera of core gut symbionts are a full 10 degrees higher. This suggests that the core symbionts have higher thermotolerance than do the parasites, such that high or fever-like temperatures could eliminate parasites without harming beneficial gut bacteria. I'll be focusing on interactions between Crithidia bombi and the symbiont Lactobacillus bombicola, a dominant member of the bacterial community in the bumblebee hindgut, where Crithidia infection establishes. To better understand temperature-mediated interactions between symbionts and parasites, I used cell cultures to address 3 main questions. First, do thermal optima differ? For this, I measured changes in parasite and symbiont growth rate across a 25-degree temperature range. Second, is there evidence for competitive interactions? Do chemicals produced by the symbiont inhibit growth of the parasite? Third, if there are inhibitory effects, do these differ across temperatures? And how do symbionts alter the optimal temperature and thermal niche of parasites? To do this, I compared parasite growth across a range of temperatures in the presence and absence of the symbiont Lactobacillus. I first measured growth rates of parasites and symbionts across a 25-degree temperature range. Here's temperature on the x-axis and growth rate on the y-axis. I found that the core symbiont Lactobacillus had higher optimal temperatures than did the parasite Crithidia. All 4 strains of parasites grew well at 27 degrees, growth rate peaked at 32 degrees, then declined to near 0 at 42 degrees. In contrast, growth rates of the core symbiont Lactobacillus tripled as temperatures increased from 27 to 37 degrees, with strong growth all the way up through 42 degrees. What temperatures might parasites encounter in hosts? Recall that bumblebees are facultatively endothermic. Queen bumblebees generate heat in the nest to incubate eggs and larvae. Queens that have initiated nest building keep their thoracic temperatures above 37 degrees. Queens can maintain these high body temperatures day and night. How about workers? Like queens, they incubate eggs and larvae, and generally keep their body temperatures well above ambient, between 27 and 33 degrees. Now let's return to those thermal performance curves to get a better idea of their physiological relevance. Incubating queens maintain temperatures that are higher than what's optimal for parasites, but great for the core symbiont Lactobacillus. The temperature of workers is within the optimal range for parasites, but the difference between the low and high ends of this temperature range could make a big difference for the relative growth rates of parasites, where growth is stable throughout that range, and symbionts, which grow about twice as fast at the upper end of the range. To summarize, the symbiont Lactobacillus bombicola performed best at temperatures that were higher than those of peak performance for the parasite, and had a comparative advantage at the upper end of the temperature range found in hosts. I then tested whether chemical exudates in the medium of the symbiont would inhibit parasite growth. The symbiont strongly inhibited parasite growth. When parasites were incubated with spent medium, in which the core symbiont Lactobacillus had been grown, growth was completely inhibited. The inhibitory effect was due to acid production, not nutrient depletion. Inhibition was reproduced by acidification of fresh medium. Conversely, when spent medium was neutralized, the inhibitory effect disappeared. I found that the parasite's growth rate, shown on the y-axis, was inhibited by acidity levels within the range previously found in honeybee guts, with strong parasite growth at the pH found in germ-free bee guts, but more than 50% inhibition of all strains at the pH of symbiont colonized guts. These experiments implicate gut acidification as a mechanism by which gut bacteria could protect against trypanosomatid infection in bumblebees. Moreover, parasite strains varied in their tolerance of acidity, suggesting that gut microbiota could exert directional selection for pH tolerance in parasite populations. To summarize, the symbiont Lactobacillus bombicola inhibited the parasite Crithidia bombi via production of acids. Inhibition occurred within the pH range found in honeybee guts, suggesting gut acidification as a mechanism by which gut bacteria could reduce infection. And parasite strains varied in tolerance to acidity, suggesting that gut bacteria could select for pH tolerance in parasite populations. Do symbionts alter the thermal niche and optimal temperature range of parasites? To answer this, I compared parasite growth rates across a range of temperatures in the presence and absence of symbionts. In the absence of the symbiont Lactobacillus bombicola, parasite growth rate was highest at 32 degrees. However, presence of the symbiont slowed growth overall and lowered the optimal temperature to 27 degrees. The presence of the symbiont had dramatic effects on parasite cell motility at the higher temperatures, whereas monocultured parasites maintain their motility up to 37 degrees. I found virtually no motility above 27 degrees for parasites that were co-cultured with symbionts. Symbionts grew faster at higher temperatures, and the faster the growth of the symbionts, the slower the growth of the parasites. Returning to the original questions, first, thermal optima were higher in symbionts than in parasites. Second, the parasite was inhibited by symbiont-derived acids, with inhibition occurring within a physiologically relevant range. This suggests gut acidification as a mechanism by which gut bacteria reduce infection. Third, the different thermal optima of the two species led to temperature-dependent outcomes of competition, with competition from the symbiont appearing to constrain the thermal niche of the parasite to lower temperatures. Having demonstrated temperature-dependent inhibition of parasites by symbionts in cell cultures, I tested whether these ideas would apply to infection of live bees. Based on my cell culture experiments, I hypothesized that higher temperature would favor core gut bacteria over parasites due to temperature-driven increases in symbiont-mediated inhibition and, above 32 degrees, direct high-temperature inhibition of parasite growth. Results in bees were consistent with what I had observed in cell cultures. Relative to the coolest temperatures, the highest incubation temperature resulted in an 80% reduction in infection intensity, and the highest proportion of bees that had no detectable parasites after 7 days. High temperatures appeared to protect bees against opportunistic infections as well. Bees incubated at 37 degrees were half as likely to harbor bacteria from the Enterobacteriaceae, which includes opportunistic pathogens of bees and immunocompromised humans. One unexpected finding was that parasite inoculation also reduced the prevalence of Enterobacteriaceae, suggesting that parasites could compete with or activate the host immune system against opportunistic bacterial pathogens. To summarize the live bee experiments, high temperatures reduced infection intensity, consistent with predictions from cell culture experiments. In addition, high temperatures, as well as parasite inoculation, were protective against Enterobacteriaceae, a family of bacteria that includes opportunistic pathogens, suggesting that thermoregulation of bumblebees could improve resistance to infection, possibly by enhancing the protective effects of the gut microbiota. To conclude, these experiments show how temperature can potentiate the protective effects of gut bacteria against parasites. Core symbionts had greater thermotolerance of high temperatures than did parasites. Symbionts inhibited parasites via production of acids, with greater growth rates, production of acids, and inhibitory effects at high temperatures. As a result, symbionts constrain the thermal niche of parasites to cooler temperatures. These findings suggest a novel microbiome-mediated mechanism by which fever could enhance resistance to infection. I thank my colleagues, family, and sponsors who have helped me over the years, the ESA for organizing the conference, and you for your audience. Please see the notes and the last slide for links to relevant articles, and feel free to leave a comment.